This is a presentation on the hyperbolic geometry, a look at polygons on the hyperbolic plane. I'm Cindy Gillespie.
I'm Rupert Cox.
And I'm Alex Moore.
First, we have here a hyperbolic person. This is just to get the idea of what a hyperbolic plane is. We're using
the Poincaré disk model,
which helps us go to visualize an approach to infinity as we get to the edge of the circle, and we use this hyperbolic person to help show what's going on so that everybody can have an idea of the hyperbolic planes we're using in our presentation. So as we move forward, we can see our hyperbolic person take a walk, and as we approach the edge of the circle, they're actually staying the same size as you move along, but it's approaching infinity, and then you eventually get to a happy ending.
I looked at quadrilaterals on the hyperbolic plane. A review of quadrilaterals on the Euclidean plane is that all the angles add up to 360 degrees. One way to look at it is through the so-called
Poincaré
disk model. One of the easiest ways to see this is by looking at the art of M.C. Escher. On the next slide, note that while the fish appear to be getting smaller the closer to the edge, they're actually all the same size, and all the white segments going from the fish's tails are also all the same length. I created a hyperbolic soccer ball and drew the quadrilateral on the one on the right, so you can see the pink lines and the blue lines form the quadrilateral on the hyperbolic plane. I also crocheted the hyperbolic plane and also formed the quadrilateral formed with the yellow lines. This model is also notes a quadrilateral using the
Gillespie notation.
The 4-6 represents 4-sided polygon with 6 polygons touching at any one vertex. In summary, the individual angles range from 0 to 90 degrees, and the angle sum of a quadrilateral range from 0 to 360 degrees.
And I'm going to be talking about hexagons on the hyperbolic plane. This is a picture of Cindy's crocheted model that is wrapped into the shape of a black hole, which I thought was pretty cool. First, let's review hexagons on the Euclidean plane. So a hexagon, each angle is 120 degrees, and so the sum of all the angles in a hexagon on the Euclidean plane is 720. And because each one is 120, there can be 3 touching at any vertex, as you can see here. Another example of this is the new floor in my bathroom. I just did this renovation this summer, and I think that these 1930s style tiles are coming back into fashion. As you can see, any of the vertices on the tiles, there are 3 tiles touching, and they are Euclidean hexagons. But there are multiple options on the hyperbolic plane. Here's an example of 4 hexagons touching on a hyperbolic plane at any given vertex. Our Gillespie notation says 6, 4, which means a 6-sided polygon, otherwise known as a hexagon, and 4 touching at any vertex. Because there are 4, each of them is 90 degrees, and therefore your angle sum for the whole hexagon is 90 times 6, or 540 degrees. Here we have a 6, 5 hexagon tiling, and because there are 5 at any vertex, each is going to be 72 degrees, which makes our angle sum 432 degrees. It's also important to note that any of the vertices you can see, you can actually count 5 different hexagons touching that vertex. Here we have a 6, 6 tiling. Each one is 60 degrees, and therefore the sum is 360 degrees. Here we have 6, 7 tiling. Each one is approximately 51.43 degrees, and the angle sum is approximately 308.57 degrees. 6, 8. Each one is 45, and the angle sum is 270. And finally, we have 6, infinity, where we have taken the vertices and they are approaching the edge of the Poincaré disk. So 360 divided by infinity approaches 0, which means our angle sum for the whole polygon is actually 0 degrees. I think it's interesting to note that as you're switching between the different tilings, the vertex is slowly getting closer and closer to the edge of the plane until you finally approach infinity, where it is actually at the edge. So to summarize my hyperbolic hexagons, individual angles theta can range from 0 to 90 degrees, and the angle sum sigma for the whole polygon can range from 0 to 540 degrees.
So this is Rupert, and I'm going to be working on the hyperbolic plane doing pentagons. I picked the hyperbolic pair of pants for my picture here because I thought it kind of looked like some 70s bell bottoms or something. First thing we're going to look at is a review on pentagons on the Euclidean plane. We have an interior angle of 108 degrees for this regular pentagon I have pictured here, so its angle sum is 540 degrees. Now, just like with the other polygons, when we look in the hyperbolic plane, we have many different options. So here we have a 5-3 using the
Gillespie notation.
pentagon on a hyperbolic plane. Each angle here has 320 degrees, because if you can count around each vertex, you'll see 3 angles at each one of them, so you get 120 degrees. So its angle sum is 600 degrees, which is greater than that in the Euclidean plane. But we can also move our way down. If we have 4 angles with a 5-4 pentagon, we get an interior angle of 90 degrees and an angle sum of 450 degrees. And as we increase the number of angles at each vertex, we will be decreasing the angle sum. Here we have 5 angles with a 5-5 pentagon, an angle sum of 360. We can then move down to a 5-6 pentagon, and this one has an interior angle of 60 degrees, giving us an angle sum of 300. And at this point, you can notice that we have the same kind of interior angle that we saw with our hexagons. So we have different angle sums, but we have similar sized or congruent interior angles. We have the 5-7 pentagon, which has approximately 5.43. Again, you can see that with the hexagon, we have an interior angle of 5.43, although the angle sums are different. We have a pentagon, which is a 5 to infinity. So each angle is 360 divided by infinity, or approximately 0. So we have an angle sum of 0, which is the same that we had with hexagons. So to summarize, pentagons on the hyperbolic plane, individual angles can range from 0 to 120. The angle sum can range from 0 to 600. And as you saw, that there are many relationships with pentagons that also work for hexagons and also quadrilaterals. Here is our reference page. I hope you guys enjoyed our video, and we'll talk about it in class.